So we have defined what is meant by the adjoint of a linear transformation T between inner product spaces. Let's next explore what are some of the nice properties of the adjoint of a given linear transformation. So let's start by observing that the association of adjoint is in some sense linear, conjugate linear. So let T from V to W be linear transformation between finite dimensional inner product spaces. So this is going to be the context. In fact, the entire week this was our context. So and let T star be the adjoint of T. Let's see, let S from V to W be another linear transformation. Maybe I should have written here, let's say S comma T from V to W be linear transformations between finite dimensional inner product spaces, and let S star comma T star be the adjoint of S and T respectively. Then let's try to see what is S plus T star going to look like. S plus T star. This is what we are interested in. Notice that S is a map from, S is a linear transformation from V to W, T is a linear transformation from V to W, therefore S plus T is also a linear transformation from V to W. And S plus T, the whole S plus T star is a map from W to V. So we are going to stare at the usual inner product that we have been using, and the property of the adjoint tells us that this is equal to the inner product of V and S plus T star W is the same as S plus TV and W. But S plus T by definition is equal to S plus T of V is equal to SV plus TV, which we take the inner product with W by the property of the inner product in capital W. This is SVW plus TVW. We will again invoke the property of an adjoint here to conclude that this is V S star W plus V T star W. Now this is an inner product which is in capital V, and again by using the property of the inner product, linear property of the inner product, this is inner product in V, this is inner product of V with S star W plus T star W. So notice that we started off with the inner product of V and S plus T star W. So this is what we have for all V in capital V and for all W in capital W. So in particular, for a fixed W for all V, this is satisfied by the uniqueness proposition that we proved after the Rees representation theorem. We have hence by uniqueness S plus T star, let me be careful, S plus T whole star is equal to S star. Oh, by the way, this is equal to the inner product of V with, we know that S star is also a linear transformation, T star is also a linear transformation. So this by definition is S star plus T star of W, which is equal to S star plus T star. So the adjointness is actually linear in some sense. At least it is additive. Let's see whether it is linear. Let's see what happens if you look at C times T. So let's see what we can conclude about C times T star. So again, we will use the same trick. Let's get familiarized with it quickly. This is just CT V comma W, which is equal to C times the inner product of TV with W by using the properties of the inner product, which I will now write it as T star W, which is equal to the inner product of V with C bar T star W, which is equal to inner product of V with the linear operation, linear map C bar times T star acting on W. This is for true for all capital V in capital V in this is true for all V in capital V, which implies C T star is equal to C bar times T star. See, this is actually, I am skipping one step. This helps us conclude that CT star of W is C bar T star W for all W, and therefore, as linear transformations, CT star is equal to C bar times T star. So, this is actually conjugate linear. That's what we can conclude about the map from L of VW to L of WV, which sends T to T star. Okay, so one observation which I would like to bring out here is that many times the properties of the adjoint can be studied or concluded by observing the identity carefully. This identity V times V in inner product of V and T star W is equal to TV comma W for all V in capital V and for all W in capital W. So this identity many times helps us prove many properties. Let's look at a few conclusions that we can draw by using this identity. So what will be the first one? The first one would be to notice, okay, so T star, the adjoint of the adjoint. Let's see what this is. So this is what we would like to conclude. So let's see a few properties. Let's try to study first the adjoint of the adjoint. So to do that, let's start with T star star. So where is T star star going to be from? T is a map from V to W. T star is a map from W to V. T star star is a map from V to W again. So we are going to look at the inner product of this in W. So let me not note anything. Let me just mention here that this inner product is happening in W. And by definition, this is equal to the inner product of T star W and V. Now notice that this is an inner product in capital V. This is the conjugate of the inner product of V with T star W by the properties of the inner product. And what is this? This is equal to, by again using the definition of the adjoint, this is the conjugate of the inner product of TV and W. But then again, I'll use the properties of the inner product again. This is just inner product of W with TV. So notice that this is true for all W in capital W and V in capital V. So therefore, what can we conclude? Hence, by the uniqueness of the Rees representation theorem, we have T star star of V is equal to TV, i.e. T star star is equal to T. So that's something nice. Oh yeah, some more basic questions. What is the adjoint of the identity? I star. Again, let's look at I star. Now we will use, so I is the identity map from V to itself. So this is an inner product in V. This is just going to be the inner product of IV comma V, which is equal to V comma V, which implies this is true for all V in capital V. This implies that Yeah, I should have been a little more careful here. Maybe I should have put a V1 and a V2 here. V1 and a V2, V1 and V2, and V1 comma V2 in capital V. Yeah, so now it is right. So this is true for all V1. In particular, I star V2 is equal to V2 for all V2 in V, which implies that the adjoint of the identity is just I. Okay, so let's just modify, tweak the problem a bit. What is going to be the... Oh, there is nothing actually to... We have already checked that this is just going to be equal to lambda bar times I star, which is equal to lambda times identity. That's one more observation. What happens under composition? Let's check what happens under... I'm using the symbol star in both, but this is not the adjoint. But anyway, that's clear from the context. Okay, let S be a map from U to V and T be a map from V to W, be linear transformations between finite dimensional inner product spaces. So I've used quite a few abbreviations here. They are quite straightforward. So we can talk about TS and the adjoint of that. Again, we're going to do the same trick here. We will look at... So TS is a map, observe, TS is a map from U to W, and TS star will be a map from W to U. So this is just going to be equal to U comma TS star W. This is what we are interested in. Okay, but then this is equal to the inner product of U. Be careful here. So this is the left hand side right now is an inner product in capital U, and this is an inner product which I'm writing just now in capital W. But then this is also a map which, let me be careful here, this is SU comma W. And I'm going to use the property of the adjoint to say that this is equal to SU and T star W. Notice that this is an inner product in capital V. So we started off with an inner product in U. This is an inner product in capital W. This is an inner product in capital V. So we are shuttling between these inner products in a very smooth manner. All right, now we are going to use the property of the adjoint of S to conclude that this is equal to U and S star T star W. Notice that again we are now in the vector space capital U. Okay, so this is true for all U in capital U and for all W in capital W. So in particular, by uniqueness, I'll not write too much and I'll just say that TS star is equal to S star times T star. This is the way in which the adjoint behaves for compositions. Okay, how about the inverse? So if T is an invertible linear operator. Now, from what we have just developed, T inverse is equal to identity. Let's apply the look at the adjoint of the left hand side. That's going to be the adjoint of identity, which is now we know it is the identity. But then this is just going to be equal to T inverse star times T star, which is the identity. This is also equal to T inverse T star. Or maybe I shouldn't do that. Yeah, at a time. So if T is from V to W, so I'll not bother writing down the domain and range. So let me see. T is from V to W, then T inverse will be the identity of W. So this is going to be the identity there. And similarly, so let me just say T from V to W. If I have to write it, this is going to be the identity of W. Similarly, T star, T inverse star is the identity of V. This means that the inverse the adjoint of the inverse is the inverse of the adjoint. That's what we can conclude here. Okay. We have seen that if we fix an orthonormal basis in an inner product space, in fact, if T is a linear transformation from an inner product space V to the inner product space W, and if beta and gamma are orthonormal bases of V and W, then we notice that the matrix of the adjoint of T with respect to gamma beta is the adjoint of the matrix of T with respect to beta gamma. Now, we were able to relate the adjoint of the matrix associated to a given linear transformation. Now, we start off with a matrix. We know the notion of the adjoint of the matrix. And let's see whether we can relate it to the notion of the linear adjoint of the linear transformation associated to the given matrix. So let's start. Let A be an M cross N matrix over F. So let me not write what F is. A could be a matrix with complex entries if it is a matrix over C. So in that case, it will be in M cross N of C. Okay, so then LA will be a map from Fn to Fm. And we know that A adjoint, this is the symbol we have used for adjoint, this is just the conjugate of the transpose or the transpose of the conjugate. It doesn't matter in which order you look at it. So you take the entries of A, conjugate it, and look at the transpose of that. That is what is our adjoint. So this proposition tells us, so maybe I should write the word proposition here because the context is this. So this, so let me not, okay. So this is just a recall for you. Then L, all this in fact. So if A is of that type, then LA adjoint is equal to the L of A adjoint. So let's see if let's see how we can prove this. Okay, so let's fix the standard basis. With respect to the standard basis, let me call it beta and gamma of Fn and Fm. This is from Fn to Fm, right? We have La beta gamma is equal to A. So what will be the adjoint of La beta gamma? Okay, so what are we interested in? We are interested in the adjoint of La star, right? This is what we are interested in. And we know that the matrix of this with respect to gamma beta, this is just the adjoint of the matrix of La with respect to beta gamma, like this. But we know what is La beta gamma. La beta gamma is A. So this is just A adjoint. But then for any matrix A, this is just with respect to the standard basis. This is just gamma beta. I'm sorry, this is just, so let me be a bit careful here. La adjoint, yeah. La adjoint from gamma to beta. This is right. So remember this. This implies that A adjoint is an M cross M matrix. If A is an M cross N matrix, the transpose is an N cross N matrix. So this is a map from Fm to Fn. So this is making complete sense. So this is equal to La adjoint of the matrix of La adjoint with respect to gamma beta. But that implies that La star is equal to La adjoint, as we had set out to prove. So in particular, if you start off with say for example, if A is something like say 1 I 1 plus I 2 3 4 plus 5 I 4 minus 5 I, let's see. Then what is going to be LA of say Z1 comma Z2? This is just going to be equal to Z1 plus IZ2. I'll write it in the column expression. This is going to be 1 plus Z1 plus IZ1 plus 2Z2. And this is going to be 3Z1 plus 4Z2 minus 5IZ1. So this is exactly the linear transformation LA. And without any uh, complications, we can just say that the adjoint of A is, what is this? This is 1 minus I 3 minus I 2 4 plus 5I. And therefore, what is going to be the adjoint of LA? This is going to be from C3 to C2. So let's see, W1, W2, W3 is just multiplication by this matrix. So let me just note down that matrix here. 1 minus I 3 minus I 2 4 plus 5 times W1 W2 W3. And we know exactly what that is. This is just going to be W1 plus W2 minus IW2 plus W3 W3. And below it will be minus of I times W1 plus 2W2 plus 4W3 plus 5IW3. This is going to be the adjoint of it. We can explore more properties of the. So now that we have seen that the notion of adjoint behaves well with the matrix associated to a linear transformation, let's try to study more properties of the adjoint by studying the adjoint of the matrices involved. So let's take let A be a matrix of rank n, of rank R. Let's call the matrix of matrix A to be having rank R. What does that mean? That means that there exist elementary matrices let's say E1 to ES and F1 to FT such that A is equal to E1 up to ES times IR000. These are block matrices times F1 to FT. I'll leave it as an exercise for you to check the following. Exercise. Check that the adjoint of an elementary matrix is again an elementary matrix. It's actually quite straightforward. You pick each of the elementary matrices of type 1, type 2, type 3, look at its conjugate transpose and check that it is again going to be an elementary matrix of the same type. Is again an elementary matrix. Now from whatever we just developed till now, this implies that A star will just be equal to, let me be careful, this is Ft star, Ft minus 1 star up to F1 star IR. So I should have been careful. So let me write 0 prime, 0 prime, double prime and 0 triple prime so that the sizes are not the same. So that's the reason why I'm putting primes there. So the primes will now get interchanged by coming here, double prime, 0 prime, and there will be a 0 triple prime. And then this will be followed by E S star up to 4. These are elementary matrices. So star doesn't, star was not the notation we use. So let me use the notation of the adjoint. The adjoint here will be the same because there are only ones and zeros in this matrix, the conjugate contributes nothing, only the transpose is taken into account, and this will be the final stage. And all these are elementary matrices, all these are elementary matrices. And by the proposition from, I think, week 6, this implies that rank of the adjoint of A is equal to R. So effectively what we have concluded is that the rank of T for any linear map linear transformation from V to W is the same as rank of the adjoint of T. So this is what we have been able to conclude by using the language of matrices. What else can we conclude? Let's look at what will be the determinant of A. So let A be an n cross n matrix. Then we'd like to explore what is the determinant of A star. We know that, okay, if A is not invertible, by one of the theorems we have proved, this implies that determinant of A is equal to 0. Also, if A is not invertible, this would imply that the rank of A is less than n, because there will be something in the kernel. And this would imply that rank of A star, A adjoint, is less than n, because it is equal to the rank of A. This would imply that there is something in the null space of L adjoint A, which is the null space of LA adjoint, which is the null space of adjoint of A, which will not be the zero subspace, which implies that A adjoint is not invertible. But what do we know about matrices which are not invertible? We know that its determinant is 0. So this implies that determinant of A adjoint is equal to 0. So this conclusion stands aside. So let's see. Let it be there. This implies that this is the implication here. Anyway, so this helps us conclude that if A is not invertible, determinant of A is 0 and determinant of A adjoint is also 0. But what about when A is invertible? If A is invertible, then we will use one of the theorems we have proved earlier, which helps us write A as a product of elementary matrices, where E1 to ES are elementary matrices. And then what will be A adjoint? A adjoint is just going to be equal to ES adjoint up to E1 adjoint. And determinant of A adjoint is equal to the determinant of ES adjoint times up to E1 adjoint. Let me skip a few steps, saying that this is equal to the product of this. But then I'll leave it as an exercise for you to check that this is an exercise. For if E is an elementary matrix, then the determinant of the adjoint of E is the conjugate of the determinant of E. Easy check. E is an elementary matrix of size n, then determinant of the adjoint of E is equal to the conjugate of E. So using this exercise, the determinant of adjoint of A will just be equal to determinant of ES bar product up to determinant of E1 bar. But that would imply this is equal to determinant of E1, determinant of E2, determinant of ES, the whole conjugate. But whatever is there inside is just the determinant of E1, E2 up to ES, which is the determinant of A. So basically what we have concluded is that if E is invertible, then determinant of the adjoint of A will be the conjugate of the determinant of A. And if A is not invertible, then determinant of A and determinant of adjoint of A both are 0. Hence, what we have concluded is the following proposition. Let A be any M cross N matrix, then the determinant of A adjoint is equal to the determinant of A conjugate. This is what we have concluded just now. What next? Let's see what we can say about the eigenvalue of the adjoint of a given linear operator. So let me conclude by proving a proposition for you. So let T be in L of V. Let it be a linear operator on V. Be a linear operator. L of V, recall, is just the collection of all linear operators on V, linear transformations from V to itself. Operator on V. Yeah. The T be a linear operator on V on a finite dimensional inner product space. That is the setup we are in. Finite dimensional inner product space. Then lambda is an eigenvalue of T if and only if lambda bar is an eigenvalue of T. So the statement of the proposition tells us that if lambda is an eigenvalue of T lambda bar, the conjugate of lambda should be an eigenvalue of T star. Yeah, otherwise it is wrong. So lambda bar will be an eigenvalue of T star. Let's give a proof of this proposition. The proof is going to be by contradiction. Suppose lambda is not an eigenvalue of T. We will prove that lambda bar will not be an eigenvalue of T star. And then after that we will prove the converse, wherein we will assume that lambda bar is not an eigenvalue of T star, and then we will prove that lambda will not be an eigenvalue of T. So instead of proving this statement, we will prove the contrapositive of these statements. Suppose lambda is not an eigenvalue of T. What does that mean? This means that T minus lambda I, this is an invertible linear operator, is invertible because there will be nothing in the null space of T minus lambda I. We are in the setup of a finite dimensional inner product space. So by the dimension theorem, it will be both injective and surjective, and therefore it is invertible. This implies that there exists S such that S times T minus lambda I is just the identity map of V, which is the same as T minus lambda I times S. Now let's look at the adjoint of this. By taking adjoint, of this, we get S times T minus lambda I whole adjoint is the adjoint of I, which is the adjoint of T minus lambda I times S. Let's use the properties which we have just studied to conclude that this implies T minus lambda I adjoint times S adjoint is the adjoint of I, which is I, which is equal to S adjoint times T minus lambda I adjoint. But what is T minus lambda I adjoint? T minus lambda I adjoint is just T adjoint minus lambda I adjoint, and we know that this is equal to T adjoint minus lambda bar times the identity. So what have we concluded? So from star we can conclude, from star we have, let's go back to see what star is. Star says that T minus lambda I the whole star times S, which is T star minus lambda bar I times S star is the identity, which is equal to S star times T star minus lambda bar I. This means that T star minus lambda bar I is invertible. That means that does not exist any vector v such that it belongs to the null space, which implies that lambda bar is not an eigenvalue of t star. And similarly, the converse is proved extremely similarly. Converse is proved similarly, and I will leave it as an exercise for you to check that if lambda bar is not an eigenvalue of t star, then lambda is not an eigenvalue of t. And with that, we would have concluded that the statement, both sides, the contrapositive of both the statements have been proven, and hence lambda would be an eigenvalue of t if and only if lambda bar is an eigenvalue of t star. Okay, so that is the relationship between the eigenvalues of t and eigenvalues of t star. So in the next week, we will study some very special linear operators on a finite dimensional inner product space, which is known as the self-adjoint operators and normal operators, and we will solve the celebrated spectral theorem for these operators in the next week. Let me conclude here.